coming to an end to this term. So not much left. I think these next two are sort of some neat lectures where we'll maybe see a more general or sort of more applications of these sort of classic simple problems that you've solved. You'll get a taste of how we can generalize them to even more problems and get an even better sense of the pressures and the shears happening in flows. So today we'll talk about what's called the Reynolds lubrication approximation. Okay? Reynolds lubrication approximation. It's a pretty famous one, and it has to do with sort of really one main thing, and that's right. We have an epsilon. We have a length scale that's really small. So shouldn't be too foreign. You've seen this stuff many, many times, but this happens to be one of the more productive approximations, and it's used all the time. Okay, so it's all about Reynolds. Okay, so it's a Reynolds approximation. So of course it's some statement about the Reynolds number. Think of Reynolds as some scale of velocity, some length scale, and then a viscosity term. It's easier to write Reynolds like this, where this term right here is a rho and a viscous term. So right, you have velocity, length scale, viscosity terms. So the Reynolds lubrication approximation, lubrication essentially refers to the length scale being small, or an uneven balance of length scales. Okay, so it refers to thin slots. Nothing too crazy. We've seen this stuff before. All right. So one way to think about this stuff is when this number is really big, we sort of reserve that terminology for Stokes flow. They really are all the same, which we've seen from the assumptions, all right? Just as the Reynolds number, however you're getting there, goes to 0, you get those nice linear heat equations, and so many good properties come from that. So that will also have that here. But terminology-wise, if this number is really large, so the idea of that the flow is happening in like a honey or a very, very viscous glycerin, that Reynolds number being small is kind of reserved for this terminology, even though they're all the same thing. I call it all Stokes flow because it's nice to have one term. Okay? This one being small, if the velocity is what's making the Reynolds number become very small, you can kind of refer to this term. This is the idea of creeping flows. Okay, that terminology. Again, all that matters is that we have this condition that a Reynolds number is going to 0 for these assumptions to hold for this model of a flow happening. But terminology-wise, it's nice to kind of maybe compartmentalize how this number is becoming small. And that's the idea if the dominant reason it's small is if the viscosity is very large, we call that Stokes flow. This is the glycerin over a sphere type experiment we did. Right? That's the shear over, right, the viscous flow over a sphere. If this is really small, that's a creeping flow, so kind of in the same realm. But this could also be thought of as those glacier flows or those tectonic plate flows, right, where the velocity is on its feet per year, let's say. So that's making it a creeping flow. So the lubrication part is some statement about length scale. So when that is getting small, really between two plates, then we're in this world of Stokes, then we're in this world of the Reynolds lubrication. Okay, so with that in mind, that's terminology. The lubrication approximation happens when you have thin slots. Okay, that's where the whole theory is based off of, right? Whole shebang, and then one thing, right? So we've done this many times with thin slot. But here's the difference with the lubrication approximation. Okay, is you would have some surface function, but this is a solid wall. So this is what I mean by thin slot. Okay, so this is what this theory talks about. When you have the coupling of two plates and one other thing that this is modeling. So when the bottom plate is moving, right? Bottom to top doesn't quite matter. In fact, one thing to realize is if both of these are moving, I could change my coordinate system to be with the moving plate, and then I would be in one case. Right? So then coordinate system like this, y, base of the plate, this will be my x. So again, then we have sort of fundamental lubrication approximation. You have some surface function happening. It's very critical for this, and that's what it's handling. Right? So notice if this function is constant, we would just have wet flow. So I'll say that again, right? In this theory, is just some height, then we would get, okay, we just took that linear velocity profile. Okay, what does that mean? I'm saying, so this is the velocity profile we should already imagine because we saw this many times. It should look maybe something like this. Okay, so again, whole theory is based off of a thin slot, bottom plate slipping. You know what this function is or some approximation of it, and there's ways to get that, but it's available to you. So this is the setup, right? So important parameters, you have this slipping velocity, very important. You have some length scale of this whole, let's say, slot. That will be my L. And then we also have some h, right? So there's an h function, right, and it will vary. So say there is some characteristic slot length. Okay, so that's also what we're going to do in this, is if h of x is some function, right, it could be a line, it could be anything. The idea is there's some sort of average or characteristic height scale in there. So we have this function will look by some characteristic. Right? And it's just, right, however variation this is, you could imagine getting it somewhere. One way I like to think about this is if you give me a function that tells me this height of the thin slot, right, I could take like a root mean squared of it, right? So in my head, sometimes I just will always think of them as like this, right? So I have 1 over L, 0 to L, the function squared, the x 1/2. Yes. And that would be, right, so this is just the integral version, integral version of a root mean squared. You want to use a root mean squared because you want to have always a positive value, not a negative value. So this is just one trial function or one way to actually calculate what these scale values are. So everything here, we have some constant thing right there. That's a good setup. It really is the setup. Okay, so then really, in this theory, we have two driving things right here, and we can show this, right? For this theory to work, we need this to be going to 0. So we have an h over L. L being really the width of this, wherever this lubrication or this interaction between two plates is happening, and then 8 being the distance between the two plates. That parameter has to be getting small. And really, you have this, call it order 1, right? Or just, it could be, we could even have moderately. So there's this phrase that the Reynolds number is moderate. Okay? So there's some, what is this Reynolds number being moderate? I thought you said that this has to be small. Well, that's the thing about lubrication, the lubrication approximation, right? Is that it's really this aspect ratio between the characteristic height, the characteristic gap size, and the L that drives the form of the equations, combined with the Reynolds number. So this can be a pretty large number, but if this number is small, we actually end up squaring it, and that kills it off. Okay? So what's a way to think about this? So let's, so even combining these things, let's just immediately see, well, what's our Reynolds number, right? So you have, if you're looking at the Reynolds number, we'll have this inertial terms over my viscous terms. Okay? So differential terms, right, we have a rho u. Okay, so that's that one, where x is this L term right here. And then the viscous term I have here, squared. Okay, so this is another way. There's always a way you can imagine what this Reynolds term is as well. Is you have this going on. Okay, so we'll have turn that into a kinematic. Okay, and then well, y, right? So then the other thing is, just from the setup of this problem, right? Clearly, right? Y is going to scale like this, and then my x will scale like that. So there's one sort of ninja trick of algebra we do right here. And you really just sub everything in there, and you'll have a u. I have here, right? And then here is an L. So the L goes on the bottom, and then it has the h squared that goes back on top. Okay, so this is the trick, right? Is you want to write the Reynolds number as you normally would always sort of express, and that's, it's just an algebra thing, right? If you're talking about a Reynolds, you have to specify which length scale you choose. So usually for a Reynolds, it's nice to always calculate that value based on the axial or streamwise flow parameters. So so the idea is like always in your analysis, just try to keep Reynolds number referring to like the direction of flow length scales. So that means, right, I would like Reynolds number to always be really, right, described as a u L, right? But in this theory, there's some parameter now that's swapping around, okay? So you just sort of rewrite this now, as you can write this exactly like so there's sort of an augmented Reynolds number for this theory, our first sort of relation for this whole lubrication approximation. And this is important, okay? So in the Reynolds lubrication approximation, because of this setup we have, you calculate a Reynolds number for your velocity, your streamwise distance L, right? And I could even write the streamwise sort of slipping bearing distance. And then you would have a Reynolds number. So these could be calculated pretty easily, right? You just know the fluid, you know the lubricant you want to use. You know how fast, let's say, a journal bearing is going to turn, or how fast you're trying to have these two mechanical parts slip and slide off each other, right? All available to you. The benefit of lubrication approximation now is there's this aspect ratio term. So that's its own parameter. And it's squared, right? So some people call this always the Reynolds number. And then really this is then, sometimes even given like an R star or an adjusted Reynolds number. But this could also be cut from scaling. But this is really the takeaway. The takeaway of this whole theory is there is now this epsilon squared term given a Reynolds number. Okay? So here's what I mean when I say the Reynolds number in this theory must be moderate. All right? So in this theory, you can have pretty fast moving velocities. This number could be, 20,000 actually. But because this number is squared, right? This number is squared, right? You could, right? It only needs to be like on the order of like 0.001, which is usually achievable, and then it would get it down to less than 1. So do I have a numerical example there? I think I have some numerical examples. Okay, so then should I leave that up? I'll leave that up. This is what's important here, so let's track this down. Okay, so how about a numerical example? I just looked up some values for a journal bearing. Okay, so this comes from an example where I looked at a journal bearing, right? You just look up a really high-speed machine part. Okay, and then, what was it, an SEA? Right, it was around this. Sorry about the units, but this is just what I looked up, right? And as long as all the units are in the same, dimensions, then it should be fine. This is 4 inches. And then the gap was this, about 0.008. So this journal bearing was right ahead. This journal bearing is pretty long. But by extreme machine part, what I mean is that this length scale, right, this H is very, very tiny. And that's usually what you get, right? So you have these smooth surfaces that can get really, really close together, and they just need a very, very tiny sheath of lubricant in them. So for this scenario, right, you have a 4, and it ended up being like this. And then I looked up the operating thing, so I just took a radial velocity, squared it by a distance r, et cetera, et cetera. So this is about 40 feet per second. That's what I got. If you can't imagine that, about 10 meters per second. Okay, so this is the example, right? The idea that you have your Reynolds number that I calculate this way, where I'll have scale velocity. Okay, this is 20. Right? This ends up being 25,000 because it's moving pretty quickly, right? And I have not referenced this H as a thing. That hasn't gone into there yet. So this is just your standard sort of the slipping bearing length, the viscosity of the oil. I think this was SEA. I think it was SEA 40 if anyone's interested, right? But they're around this feet per second. Okay, so this is 25,000. And then wonderfully, right, you sort of confirm in your head, you take this ratio, right? And that was my epsilon. Okay, so then my epsilon, right, it was 0.002 inches, okay, squared, right, you get 1.0000004. Okay, holy camole, right? And then, sort of for the lubrication approximation, this quantity is less than 1. It's an order of magnitude less than 1, so I'll get my Stokes flow relationships. So that's the idea, right? You have these length scales that could be fairly moderately big. You could have a speed that could be moderately large as well. But when it comes to this thin slot situation, this is what happens. This term dies out quickly because of the squaring that's happening in that small expression. Okay. So let's see it through scales now. Let's see the same situation through scales. If you're bored of this, I figured I wanted to do another one because many people are still confused with doing this scales. So I'll throw up another example, and you can see how all of these things I'm doing can be done through scaling the Navier-Stokes equations. Okay? So from the get-go on Reynolds lubrication approximation, you draw that diagram. Outside assumptions, right, is we're going to have it be a 2D flow. That's what we're going to say first, right? And it's not the worst thing about it. At this point, you should understand 2D flow is a really good place to start, and has very far-reaching consequences, right? And then we'll also say it's a steady flow. So those are just two right off the bat things we're going to say, and then we can write down the dimensional Navier-Stokes equations if you want. Okay, so equations become. Have conservation of momentum. I'm just doing a shorthand right now, so you don't have to write these fractions. I just have this. This is the partial operator with respect to x. This is u. Partial operator with respect to y. This is the v velocity. So v is the y direction velocity. U is the x. Okay. Thin slot. Here is the slipping boundary velocity. Again, the theory is based off this idea that the bottom plate, or one plate relative to the other, is moving and slipping. Because obviously we're lubricating something, so you're going to have slip between mechanical parts, stiff mechanical parts. Okay, here's my h of x. Also solid, it's also very important. So right here, I have, say, v, u. And then you just have all of the Navier-Stokes equations. And you write them all out. Boo-doo-doo. U. So there's the x momentum, and then we will have the y momentum equation, and you'll see the same thing happen. that you did for boundary layers. So I'm doing this again because I want to show everyone in this class that the same things happen over and over and over again in fluids, for the most part. A lot of patterns have been seen by doing lots of analysis. Okay, so I spent a bunch of time when I wrote down every single Navier-Stokes equations. I'm not doing my operator thing because I think people like to write out people certainly in class like to write out all the scalar parts, so I'll just do that for you. So we have conservation of mass as the continuity equation. This is the incompressibility assumption. Then we have the 2D of U and V written down. Okay, what are the scales? Well, I already put them up, but I'll do it again. So the only scales given to me is the x will be a length scale L, and then the y is going to be what? An h naught. So I know these things. Right? So where do I go from here? Where do you go from here? So I wish I had an actual classroom because I'd like to probe people to see if they're getting it. I think everyone's getting it, but then fundamentally I want you to kind of maybe see, right? Draw a picture, make some basic assumptions. You have the length scales as L, length scale Y is with H. Then you write them all up and you say what? First go, what the heck do I not know? Well, I don't, right? Well, you go, well, there's a U, a V, and then there's a pressure scale. Okay, so just, right, this is the naive thing. I just write those down and I go like, well, I know x scales as L. That's really my natural x coordinate. I know y is basically around h. So you go, what's the U? What's the V? What's the pressure? Okay, so you could, you could go, well, I guess I know I have 3 equations, 3 unknowns. But again, when you're looking for velocities, I've said this many times, right? To start off with velocities, you have to go to your boundary conditions or initial conditions. It's a good place to start. So, I mean, even with lubrication theory, you should see, right? I think somebody in the class would go like, well, I have a U scale, right? U is around this slipping velocity, right? Not slip. It's not like there's no slip, right? The sliding velocity of the plate. Okay, so the U velocity is this boundary velocity U naught, right? It's the prescribed velocity of this mechanical slipping between 2 plates with a lubricant between them, right? So this is going to scale. Okay, not slipping. I don't want to say slipping because it's not right, because no slip is still satisfied. So I'll say this is really the sliding. Here's my sliding velocity. Okay, that's fair. Anything for V? Don't know it, right? I got nowhere to go with V. What have I told you many, many times, right? The whole point, right? Got to use continuity, right? Stupid. Right? The idea is when you have velocities that you don't know, you're trying to relate velocities together. You're solving for velocities. You do that using continuity. Okay, pressure scale. Well, at this stage, you could actually just know what to sub in for pressure scale. But, I mean, for this, we could solve for it, right? Right? So the idea is, it's still really what we did is we turned it down to 2 equations and 2 unknowns. We prescribed the x and the y scales because we drew a picture and saw them. We wrote down our equations. What I didn't write down were the boundary conditions for these equations, which really illuminates where everything's happening, right? So this x momentum equation, right, has a boundary condition. What? Hello, Slack. Here's my code. There are no changes in one ratio. Okay, so there's this thing where at the U, what's the boundary condition? Well, there's a boundary condition that U at 0, I want to equal the sliding velocity. What's the other boundary condition for this equation here? Well, I have U at h. I know h is a function of x, so even, call it a dynamic. So U, when I'm at the actual plate height, there I have no slip. Good? Same thing here. My velocity here, there's no suction happening, although you could do it, right? So in this whole theory, we can also have lubrication between porous plates. where the porosity is causing some small suction or causing some very tiny velocity here, throw that in the equation, you can still do it. But for the classic stuff, you don't do that. So this is 0. And what else do you have? Boom. That at x, also 0. So here's really all the full sets of the equations. Right? And here you go, OK, what's a U scale? Boom, found it. V, shit, don't have one. Use continuity. Pressure, what about pressure? Well, at this stage, you all should maybe have some reasoning of how to get the pressure scale. What's most of the energy happening in here? But that's where it gets kind of weird maybe with the Reynolds stuff, because intuitively maybe you would say, well, it's viscous dominated, right? Where I'm assuming it's really viscous dominated in this whole system. So you want to really say, you could say this. Right? If I have a little box right here, I would look at what's the work done, right? What's really most of the energy in this little box right here. You're going to say, well, it's really the work done by the viscous forces, work of friction. That's really most of the energy, and that's your pressure scale. Pressure is energy per unit volume. I should test you on that. What are the units of pressure? Pressure is energy per unit volume. Never forget that, please. Okay, so with the pressure, you would say this, but you'd be wrong, right? You'd be wrong because if you do the full scaling, you notice that it's actually by a factor. We get a different factor in here. We get an epsilon there. Anyone see some craziness happening right there? Okay, and and you can do it when we solve these things. Okay, the main difference then of the lubrication approximation is really that term right there. Okay, this one is just boundary layer. Nothing new. Seen it. This is the new part. The new part of lubrication approximation is the pressure scale, right? It jams and blows up. It blows up because epsilon's really tiny, right? And it comes out, right? And it comes out from how you get this, right? From how you're getting everything to balance. So what does that mean? Well, let's do it. Okay, we're on the hunt then for V and the pressure. So let's not do that, right? You should all see, you've done it in homework, you saw it in boundary layer, you can get the velocity, right? You fucking scale this thing and then find the V, right? So then here, what do you get? Boom. There's a V scale. Recognize it? Same thing with boundary layer, right? The same situation. You make this a scale equation, you go U naught over L, then V over the H. You solve for it, you get this epsilon term in there. What's it mean? It means there's really, in scale terms, right, it's so small that there really can't be that much velocity going up, or else continuity would not ever be able to be satisfied. Okay? If you had a lot of velocity going up from the bottom of this plate, it would become three-dimensional because it has to go somewhere. Okay? And that's, right, in some sense, what ends up happening. So that's the velocity scale. How about we look at then just the full pressure equations, right? We just look at the full scale. So term by term, you plug everything in, and we get scale. This is scales pressure. And then scale. So this is x. It's the y momentum. Okay. I use these commas because it's just kind of quicker. I don't have to carry around a bunch of star derivative notations. But really, right, there were 5 terms in all the momentum equations. Here's the coefficient in front of the first non-dimensional inertial term, coefficient in front of the second non-dimensional inertial term, coefficient in front of the non-dimensional pressure term, coefficient in front of the viscous terms. So the commas just maybe help you write this stuff out faster. See, you're supposed to do it, but it really is just sort of, right, kind of, right. So maybe I should say this is x momentum. This is y momentum. Okay, I already used the continuity equation here. Yes, and you get this from, you're getting this from, see the pressure rate? Hold on a second. I lost an L. Sorry. This one is divided by, sorry, 1 sec. I just caught something. There'd be an L down there, there's an H down there, and this would be a mu. This, okay. This would be, okay, yeah. So I missed an L in the notes. Got it. Don't do stuff by hand. Just always do mathematical, please. Point still stands. And then you get this y momentum if you did it by hand. What really you do is you multiply through the entire thing by a 1 over epsilon. You multiply the whole thing by an epsilon because you really have a 1 over epsilon term in this pressure term. So you multiply through, you kind of see the relations in terms of all epsilon by epsilons. It's kind of not really supposed to do that, but like, right, okay, let's just do this. Okay, so then here, is the H. So now you see, right, here is really this whole pressure scale now coming about. Okay, the order 1 term of x momentum, I have one variable, right? I have one term, and it's the viscous, right? It's the viscous pressure in the y term. Makes sense because there's a small length scale in there, so the most curvature has to be there. So I have one here, right? But what have I said? You can never scale away your pressure. Something has to be driving this. I need pressure in there somewhere. So that is this conclusion here where you find the pressure scale, right? This equation, right? Because as, right, you want, right, as epsilon's going to 0, so here is an epsilon. So as epsilon goes to 0, right, I would just have, right, only this term retained. There'd be no balance in the equations, and that's not OK. So that's this conclusion of what the pressure scale is. The pressure scale is coming from when I did my non-dimensionalizations, I have all these coefficients. I go, OK, a bunch of Reynolds numbers, a bunch of epsilons. I'm going to make epsilon drive to 0 and have Reynolds moderate, right? So when you get this situation, now you say, okay, moderate. You could really just say, right, that Reynolds number is finite. Okay, that, right, mathematically that's allowed for you to do, and all these conclusions are holding. So I let the gap size drop down really, really small and just have a bounded Reynolds number, right? The big thing is that I have one here, and everything would drop out. So to fix that, then you go, okay, well this has to be order 1. And that's where the pressure scale is coming from. So that means in Reynolds lubrication, my pressure scale is this. It wasn't the L. The pressure scale is, sorry, I never should have put the L there, actually, because it's always the, okay. Just go back to the Poisson flow, or Poisson. I can never speak French. I'm really sorry, wife. Okay, so this is it. And hopefully I just did it in front of you that you get and see this idea of how the scales told you that, right? It's not intuitive that the pressure scale is a 1 over epsilon term in there. And everything from this point on really is dependent on this. All the conclusions we do by doing solutions and solving them and finding out the actual pressures, it just really tells you this. that the pressures involved in lubrication theories have a 1 over epsilon involved in them. Right? Epsilon is very small, so this is enormous. It ends up being enormous. Fascinating just through scales. Big takeaway on this idea is right, concluded because something right? You conclude that because something has to be driving the motion in the x momentum equation in the limit, right? In this situation right here, the order 1, right, in this situation here, the order 1 term then is just the pressure. Pressure can just exist, right? The pressure can exist on its own. There can just be, right, there can just be energy in there, but the motion has to balance some, right? The motion has to be balanced by some pressure term. So if that's not clear throughout this class, just maybe reiterate and write it down a bunch of times. You can't scale away pressure when it comes to motion. Pressure can exist on its own. If you have motion, something has to be driving it. I'm going to test you on that. And do I have all my equations? Okay. So, right, all of this scale stuff to say, right, big conclusions are what? Well, the governing equations then of the Reynolds lubrication approximation, right, are the same wonderful linear Stokes flow equations we have. But they're like that for slightly different reasons, and that's what's important to know about when it comes to this theory. They're driven by this length scale difference. They're driven by a small gap existing. Right, so the equations of motion then, right, so the equations, right, the full equations are still continuity. Right, dimensionally we have then continuity, right? This always has to exist, right? I threw a term away essentially because I'm saying 2D. So that's the only way you can get rid of a term in continuity is if you assume 2D or 3D. If you assume 3D, I have an extra term. So I have that, and then you have look familiar? And then you have this. So that's what all the assumptions boil down to, just that in the 2D case, in my 2D case. Same theory can be extended to 3Ds, and we'll do that later. But start here. Start small. So I have conservation of mass. X momentum turned to just this simple equation. Y momentum turned to this equation. This means all the order 1 stuff. So 1, 1, select only these terms, and then this is now order 1 as well. Right? Did I have this right? Because if I put this, the pressure scale back in there. Pressure epsilon there. Yes, because when I plug this pressure back in there, it turns into order 1. Right. Oh, yeah, because I multiplied through, I think I multiplied this expression through by an epsilon, but I didn't do it on that term. So now when I insert this pressure scale into here, everything cancels, and this just becomes the value 1. Okay? Now the pressure, right now the pressure being order 1 is fine. That just means hydrostatic. That's just like hydrostatic pressure. No motion, just pressure. That's the idea, right? Thermodynamic, right? So hydrostatic can exist, right? That's the idea that fluid can just be at rest and the pressure still exists. So you can have this term be 1 with no motion. But if there is motion, there's got to be pressure. Pressure has to drive it. I can't have 1, 1. Some pressure had to drive it. Even the boundary layer, you had to retain that term. Okay, governing equations. Boom, here they are. What's important? I will test you on this. Why do I write an exact derivative on that dp dx? Okay, I write that because of this equation. Okay, I will test you on that. Okay, the pressure is only a function of x because of the y momentum equation. That is a big trick in the fluid analysis, is you write out all the equations, and if one of them looks like this, you go, aha, well, pressure is not a function of y. That's what this means. So that means I can write now a dp dx, exact derivative. And then really from here you go like, okay, actually that means this is an exact derivative as well. So you get your ordinary differential equation. Okay, so this, and then I have pressure here. Okay, that's the setup. So what's different then? I just did that, right? We did slot flow way back in the day. I already did this problem. No, what is different this is what's making it different. Okay, the lubrication approximation really is an extension of these slot flows. You just now have this varying plate, right? There's some surfaceness of this plate that you prescribe to the equations of motion. When it was just a 2D slot, you're solving this system, but you don't have this. Okay. So how do we go about handling now this H? Well, you really just kind of go about it the exact same way. Okay? It's still the solutions that right? It's still the integrations and everything that you've done before. Only now you just put an h of x everywhere. Okay? So there's some trickery with that, and it really makes u a function of x and y. So there really is a partial here. So that's really what I should write. That's really important, actually, is you can't write this. It ends up, because of this, you have this. Okay, so this isn't actually a partial, because u would then have to be a function of the y and the x. Like, right? So quasi-steadily. Okay, so then how do you go about solving this? Well, you do this thing called integrate. What you end up doing is you have this integrating continuity. Okay, here's this, something like that. So this is the h of x. It could be curvy, however you want it. So then here's x0, L. Okay, let's say there's some flow rate then, Q. That's my volumetric flow rate going into this slot. What does that mean? Okay, so in this theory, right, that's the major difference, is you can calculate what Q is, right? And it's going to be that, right? So what the heck's different? What's different now is this upper integration bound, because this is now changing. Before it was just integrate all the way up to h. That's what the flow rate is. Bada boom bang. This is now a big thing because, right, since it's incompressible, this is a constant value. Okay, wherever I take this x, then this would it's going to equate. The flow in is equal to flow out no matter where I am. So in the integral sense, that's your conservation. Okay, so, and we'll use this later. But for now, what's the solution of this system, right? Okay, this comes with the boundary conditions. What? I have that. Okay, and then what I'll have at the top. Okay, this is the sliding. And what is this? No slip. Those are your boundary conditions. I want to point out with this theory how general it is, though, because even if I do have these both sides slipping, I could just change my coordinates, right, in a Galilean transformation to I'll change my coordinates such that I'm like riding along on this plate, and I would still have the same coordinate setup, right? So even if both sides, right, even if this one's sliding and this one's sliding, let's say you did something like this. say this one slides this way, this one slides that way, you could just transform your coordinates to then get back to this scenario, because it would just be the difference that matters. But not important for the general thing. I'm just wanting to know, I want you to understand that this setup is very, very general because it handles even two of them slipping relative to one another. Keep in mind this. This is important. The idea that Q is a function as I go to H needs to be constant at any x that I pick. So now you write out the solution for this with these boundary conditions. We've done this before. Okay, it's a superposition. This. Boom. Just writing it like this. Okay, wait around it. Yeah. So I know there's an h could cancel out. Okay, but you write it this way because it's nicer to see this y over h, because this would be a non-dimensional y, non-dimensional y, non-dimensional y. It's really why you're sort of doing it this way. Then you have this classic representation right here, and it checks out. Okay, so this is the solution. You get the solution by just doing all of this junk. Okay, important parts. Think about this is we already know this, right? The solution for the situation, right, even though h is a function of x, you still plug it in this x value, and now it's a superposition of just linear flow with quadratic flow happening. Right? So if you kind of draw these out, you get this situation where it's sort of like this. It could be flows that look like that. Or it could be kind of a little bit quadratic-y. And even could actually get some backflow happening here. Even look like that. That's just from playing around with this. You've already done this, but it's really at any x. So you pick one x value, plug it in for the h, and then the solution looks like this locally. Now let's move into sort of more of this lubrication. Haven't really done anything new. This is now the new part. The new part being here, Q. So what's this flow rate? Well, you calculate that now using this up to this h value. Q this is what I got. Okay. All right. And now solve for this. Okay, you just rearrange and now solve for what the dp dx is. And that's when you get this dp dx. Looks like this. This may seem like lots of steps, but I'm sort of doing it this way to show you something later. Okay, so now this is now a function of x, because h was a function of x. So the pressure gradient in the x direction, importantly, we already got from scaling there's a 1 over epsilon term, right? Everyone remember that. So importantly, from now, I just did some analysis. I just wrote out the solution given the system that I have, and now I'm doing some trickery. Trickery is I calculate what the q is, and I have it as a function of x now, right? So now q being a function of x, constant retained. Now I'm solving for what this dp dx is as a function of x. That function now is proportional to viscosity, but now there's a battle between, right? There's a battle between sliding and flow rate, right? There's a difference term in here. Everyone see that? Just from how I solve for dp dx, I get the situation right. Keep these as function of x. Okay? Maybe I'll just do that. So this is sort of, think of now, I've solved now for what this, right, dp dx as a function of x is, because it's this, right, as a function of x squared, height as a function of x squared. Okay. Why can I write this q here? I can can write the q here because the q is going to be constant no matter what x I have. So I could write the q right at the, let's say, x equals 0. So what's the height at the inlet? I could write the q as the outlet. I could say, well, how about the, how about I'll just write out, I'll figure out what the flow rate is at h, right, at h of L. Doesn't matter where it is, but you could integrate and find a q value. That would be your volumetric flow rate. And then there's this sliding velocity. So already here, this is the sort of big takeaway, right? Because of the minus, we know right, because this could be 0. That's what's important, that this could now be 0, so that means that we know that some critical pressure is going to exist. There's going to be some either maximum or minimum pressure that's going to exist within the slipping bearing. Right? And that's what we care about, really, is that maximum pressure. You already basically know what's going to happen because you did the scaling of the Navier-Stokes equations. You know that the pressure is going to be enormous, more than what you would have prior, because there's a 1 over epsilon term in there. So no surprises coming your way. You're just seeing these math steps that people did back in the day. This is still a nice relationship, though, because I like this one because you do have this x, so you can just kind of put in any x you want and play around with this. It's kind of fun to do, right? You could do a crazy x, right? Desmos it. Or I think Mark has recommended GeoGebra. Correct me on that. There's a GeoGebra program that's like Desmos. I like Desmos. It's just kind of quick off the ground. There's like 0 learning curve, I think. But Mark did recommend GeoGebra. GeoAlgebra? Something like that. Also fun to play around with expressions like this. Okay? Right? See what happened. Right? This is a parameter, and now just plug in any function you want. And you're like, interesting. It is interesting. So we're not quite done. There's another trickery thing you can do, and this one I like a lot as well for this lubrication thing. So integrate. Now we integrate this equation. And that would give me the pressure as a function of x. So now I have pressure through the journal bearing by just integrating that last relationship. What do I get? After some integration, you all know how I do integration now, right? I shared my Mathematica notebook, and hopefully you notice. Do it all in there. With one caveat, right? What happens is I let Mathematica do the integration or desolve if it can do it, and then if it can't do it, now it's on me. I got to do some math now. But if Mathematica can do the integration, let it do the integration. But now I take the output and then I rework some algebra with that to make it look cleaner. Because some of the outputs Mathematica gives you are fucking horseshit. So please do that. Please don't just plug in the output of Mathematica if it doesn't look nice. Almost always you can rework it to make it look good. Now this is super cool, right? This is super cool. Okay, everything's coming from in this boundary, in this theory, right? Again, it was just slot flow we're doing. I'm just letting x change, right? Okay, but this is super cool, I think, because now you have this q relationship. We're going, well, if x is varying, I can calculate a q. I can do a q. That will work. The q will be constant, so now I can use it as a parameter, get the pressure integrate. And now I get this really neat sort of term, which is really the characteristic height. So this is an example where you don't really know what h0 is. You just say, it's around here. I said it could be a root mean squared, but that's just an estimate, right? But the really actual h0 in this case, you can calculate at any time. Gorgeous, right? Okay, so do this thing where we're going to go, okay, well then, pressure at the outlet, I'll just say is my gauge. P0. Hello? Hello? Someone out there? I should lock the door. Okay, this is just saying that the pressure at the outlet and inlet of, just atmospheric, let's say, right? The pressure at the outlet inlet of the slipping bearing should just be the same. Okay, and then when you do that, you then solve for the flow rate again. And then you get a neat relationship now. For Q, oh, Jesse's dropping. Scared the shit out of me. Okay. This may look pretty nasty, but it's really not, because what you have now, right, is the characteristic height. And that's what you call this expression. Called capital H. I should say H naught. I have a bunch of capital H's in my notes. Okay, right, or. Okay, so this is the volumetric flow rate per unit width. Okay, and this is it. This ratio of the integrals for whatever hx you have, keep in mind, right? Numerically, you can figure this out now. Beautiful. Okay, and what you've done now is, through some analysis, you actually figured out what the actual characteristic height is. And it's dependent on this h. And now, even cooler, you can play around with how curvature of your h's really affects this. Pretty cool, right? So now this is the h naught. This ratio, this 1 over h things, gives you the characteristic height. Pretty neat. And it really allows you to write the Q, the mass flow rate, in this very simplified way. Okay, you'll know the actual volumetric flow rate of fluid moving through the bearing, right, because of this sliding thing, based on this. All you got to do is know your sliding velocity. It's usually a design variable. You say my shaft is rotating at so many RPMs a second. That's inducing a sliding between mechanical parts. You know what U naught is. So what's the right? So you kind of figure out, well, how much mass flow rate of lubricant would I need to needs to be in there? How much ingestion of liquid is this slipping bearing taken in? Boom, right? Just boom. It can be anything. You can do surface roughness. Calculatable. And now you sort of back up, and you can get a different expression for the pressure gradient now. Okay, so now in this context, now there's a pressure gradient, and it's just another way, basically a more useful version. This one's kind of nice, right? It's because you have this flow rate in U. This one's just a bit better because you always really know this U naught. Okay, you always really know what the sliding velocity is, and always in this theory we're assuming that you know what this top plate function looks like, or you model it some way. Okay, it could even be an interpolated function. Right? You could even take like a little laser and drag it across the surface, let's say, and figure out what that is. It's usually just h. You could do it, right? And then you would get this, calculate what this h naught is. Everything falls really from that, and you get it, and you did it from your brain power alone. So did I have those in here? Anything else to say? Okay, big things about this, right? You have this 1 over hx in there. Okay, and then here's this 1. Okay, here's this 1 minus. So here is really, you can kind of see where. Okay, so now here, pretty easy to see. I'll call it critical. This, right? The pressure gradient is equal to 0 when what? Well, that's when this is equal to 0. Right, fascinating, right? And the idea is, it even tells you, right, if this happens prior to getting to the end, there's going to be some maximum bound in there. Okay? We're not quite there yet, but really what we're concluding is you can figure out where the maximum pressure is with this theory as well. So then along here, if here's the bottom plate, this is what's going on. Here's the slipping bearing plate. And it's sliding at this. If I make a pressure graph now, here's pressure. Okay, this equation now is really telling you, if you plot a bunch, something that looks like this. I can calculate that critical value here. And importantly as well, once I have the critical x thing, I plug it back into the pressure equation right here. And then what are you going to get? Well, then what you're going to get is then this maximum pressure. Okay, basic calculus. But importantly, the program is really there. And then you would know what that pressure is, what the maximum pressure is in your lubricated slipping bearing. And it's not that bad. It's not that hard to calculate now, especially if your computer calculate these equations. Okay, these equations are much easier to calculate than just throwing the whole thing into a CFD solver. A bit brutal. So what else? So now this is right. So what I've done now is I've made no assumptions. Importantly, that's what's important, what I've done right now. Everything up until now is general enough for any h of x you want to draw, depending on some things, right? There are certainly restrictions on this value if you have like a non-differentiable h of x. But come on, don't be that guy. Okay, even if you have an extremely wavy surface, this stuff would still basically tell you the correct answers. You would have eddies, or you'd have those Moffat vortices happening on the top panel, but that wouldn't affect this actual pressure gradient part here, because you would still calculate it all through this expression here. So now let's make an assumption on here, and this is critical, right? This is important. Now we're going to do really this, right, the slipping bearing, or really have this sort of fundamental or canonical slipping bearing or sliding bearing problem, and that's when h of x is equal to a line. Okay, so let's call this is one way. This is a way you draw this. So. Here's L. This would be H2. And then up here, H1. Okay, so here is the actual slipping bearing. It would look something like this. What else do I have? It's all in here. Okay, so here's the sliding plate. It's moving at a u0. Okay, so this is the classic thing. And then you have this slope, the delta there. And then this is the actual A. So if you take this line, right, and you draw it further out than where the actual end of it is, or the exit location of this is, it's just a very easy way to write this line. Okay. All right, so then just from this and all the equations we have prior, right, I told you I made no assumptions on the hx. So now let's plug in some values of hx and see what we get. And then you get these types of equations right here. So the flow rate through there now will be the sliding velocity, my slope parameter, and then like this. Okay? And importantly here, all these things are now just parameters you have. Right? And at least if you had a pen and paper in front of you, certainly not that hard to calculate. And then, right, so again, all I'm doing now is I'm just plugging in a specific h of x and everything I wrote down before, right? Yes. I even need to put this. So I have an h squared in there because it looked a little better, but how about I just write it all out? Okay. All these equations are just coming from what? They're coming from me they're just coming from me plugging it into Mathematica and go like, all right, what does it look like for a line? Okay, so now I have a pressure as a function of x. So now I can actually calculate what the pressure is on the inside of this sliding bearing, and I can also calculate what the flow rate has to be. Okay, what is flow? And the other thing is like, where's this flow rate coming from? What do we mean the flow rate? Okay, the flow rate is this idea that in this thin gap idea of lubrication, you have a sliding plate, and the viscous forces are dragging fluid through here, right? So the flow rate is exactly characterizing that, okay? If I slide this plate, the viscous forces due to no slip, right, have to stay at this location, so they're dragging along through there. And you're asking, well, then what's the flow rate through this situation? Okay, what you have is on the interior of this thing, you get a velocity profiles that are looking like this. That, and then on the outside and then on the outside when it exits, no slip on both sides. Right? So this is sort of the idea of you have an exit where it's no longer there. This is an idealization, but this is that flow rate you're talking about. Really, these areas, right, and the idea is that these areas are equal. Okay, and then in the idea of the pressure, what happens is the pressure graph for this sliding bearing has this almost arc, but it happens a little bit later. So it has a little blow like this. So notice that at this critical point, right, it's not halfway through the plate. And we know exactly how much it's not halfway through the plate. So really, you could be done there, but we can do a little bit more if we just rewrite things. Okay, so this is a nice way to write it, but there's a longer format to write the equation of a line. Who'd have thought you'd be taking an advanced fluid dynamics class, and we're talking about how do you write an equation for the line? But it's not right? It's a non-trivial thing. The way you write the equation for a line matters. It tells you and lets you express your ideas differently. Okay? Just as people harp on people to, I'm getting too hot. Just as people harp on like, hey, make your thoughts clearer when you write, and people edit your writing. People seemingly don't do that with math anymore, and they should be, right? Because the way you write a line can be helpful in different ways. So let's do that. Let's write the line differently because we're trying to express our ideas in a clearer sense. Okay? So I also can just write the line if I talk about the inlet and outlet heights. Okay? Here's the H2. Here's the H1. Okay? And that's just really, right, you have everything sort of in there as well. When x is equal to 0, I equal H1. When x is equal to the length that I have, this becomes 1. Minus, minus, I get H2. Bada bing, bada boop. Got the right equation for a line. But this idea now, if I'm only expressing it between the inlet and outlet heights, essentially lets you write things in a clear format. So now you can even write a parameter. Yes. So I could pull an H2 out, and then I would have this k plus 1 minus k. And this would be my non-dimensional x now. Okay? And then you've just defined now this k as being what? K is H1 over H2. Okay, and in this sense, this is a number that's larger than 1. I've defined it that way. So now we go through, we can calculate everything in terms of this. Now I just want to throw them up there. So then, it might not seem like it, but then here's the pressure as a function of x along the slipping bearing. You have your reference pressure, and then a 6 mu this, and then this ratio here, so L. Okay, so everything you're seeing right now notice that we always have this 6. We always have this 6 mu u popping up. Remember from Stokes' law, that was very fundamental for the pressures or for the forces over a sphere in flow. No, it's even still popping up here, right? So that's really it really is fundamental and shows up everywhere. So this pressure as a function of x now, we see even more revealing itself now. I didn't write the k in there. K comes later, K comes later. Okay, so now we see this top ratios and then this thing right here. So this difference now in the square difference is what drives this pressure. So this is really sort of your epsilon version that's coming up now. And really, this difference is here. More so plot this. So this is a nice thing if you Desmos this and even put the h of x back in. You can see a bit more. I know I said it makes your ideas clearer, but it doesn't make it quite clear until I do something next. This now helps us calculate net pressures and net shear forces. Net pressures, net shear forces. And that's a quantity that certainly would help us. Okay, remember what k is. Simply because you have these h of x's retained in there. All right, so now let's get to lubrication theory. It's really why it's called lubrication theory. Okay, let's do this now. Let's look at this net pressure. So the net pressure, what in the heck is net pressure? Integrate all the way to L, my pressure function, dx. And use the one I did last time. Here's your 6 mu naught squared. And now I have this k value. Bear with me. Oh my gosh, is every fucking marker dead? Every one of them? Use these that long. Okay, so this is the net pressure just through integration. And now I have my parameter k. Again, what was k? Okay, the k being h1 by h2, number that's greater than 1, which is important. Okay, and then one way to think about this is this just looks like function of k. Only a function of k. That's sort of what I'm getting at, this parameter thing. That's really your, that's really your driver analysis on really what this net pressure thing is. Analytically calculate it too now. Okay? So I have the net pressure integrating it. Now this f of x is really just lumping all of these terms together. Okay, everything with a k in it is now a one-dimensional function with just the parameter k, and everything outside. Keep this in there as well. Okay, really, you could even divide out by this, and now you'd have a non-dimensional net pressure, right? So you could even have non-dimensional pressure. How would you get non-dimensional? Well, you would just, so then you could even have as that, right? So now you have the non-dimensional net pressure. I've just divided all these expressions out by this, whatever the pressure is. And it's still the same pressure scale. It's exactly the same pressure scale we got from the scaling as well. So all good. But the idea is, boom, you got the function now as a parameter of this flow slope k. And I can do the exact same thing for the shear force. Okay, so now I do the same integration for the shear force. I'll go with the force on the wall. What is that? It's just this integration. Integrate all of the shear stress from 0 to L and figure out what the heck that is. Okay, I want to leave that up. I want to leave this whole expression up. Okay, so this is what you're calculating. And then you get the net shear. What do you get for net shear? Well, you get even more stuff. And the more stuff you get here is now HC, blah, blah. Now I have a k minus 1 not squared, H2. And then I get a 4 ln. I even actually still had to do some reworking of this. Okay? I still had to do, I had to take what Mathematica spat out, and I had to re-algebra it to make it a little bit nicer to look at. All right, who the freaking heck cares? It cares is this, right? The idea is now with lubrication theory, I can tell you my coefficient of friction. Right? How good, right? How, right? What is, let's think about the ratio now of shear over pressure. What's the ratio of all of the shearing forces on my walls to the pressure outward, normal? So that's what is the tangential forces, net tangential forces due to net normal forces, that ratio. That ratio you calculate now. So coefficient of friction would be, shear, exactly this. And then I just have this. This is an ln k, so this is bigger than this term. Right, so then, and then really this is, just think of it as, okay? So now I have the coefficient of friction, and I have it as a function now of some of the outlet slipper bearing height, which is the smallest one, the length scale of this bearing, and then just this ratio, this function, it's a ratio of this function that is this non-dimensional function is only a function of the ratio k, and this is k. And you know that k is greater than 1 really on your formulation. And now you can really tell, right, this value. So this can be made very, very small if I have a very tiny gap. And also can be made small based on k. And I implore you to actually plug that in. No one's going to do it, right? I think everyone's like, but it's fun. At least you can write these things down. You can plug it into Desmos. So you can go like, what's it do if I tweak k around? And you can see you now have two design ways to get this coefficient of friction as low as you want it within your means. Right? You can either make this ratio larger or smaller, right? Or you can just make that right, or you can just make this extremely tiny. What else? Point of maximum pressure. Okay, and then also you can calculate the point of maximum pressure. Point of maximum pressure. Point of maximum pressure. Remember the x critical and all the same equations now. You can take that p of x and solve for values of k, right? You solve for the x critical such that the derivative equals 0. I think you've done this before in calculus classes, so I don't want to go through it. You also can just jam it into Mathematica and say, tell me the point x such that the derivative is 0. This is awful, right? But I'm doing this on purpose. Okay. Yes, yes. And this really tells you, right? This is the x critical part. This is in the pressure thing, this XCR, right? So where is the maximum pressure? That will tell you where, or where the most this wedge is going to experience the most normal force happening on it. So that's going to be this pressure term here. That's going to be the pressure curve where the maximum is. Okay, this expression right here is always greater than 1, depending on the sign of k. If k is greater than 1, this value expression is always greater than 1. It's important. Okay, so this is really telling you, right, so the maximum pressure is always a little off of the halfway point. And exactly how far off is you can calculate it based on this thing, right? So again, you just redefine things. You can always tell where the maximum pressure is by, some g of k. You program this g of k thing, you go like, well, my ratio is this. I'll tell you where the maximum pressure is. Bada bing, bada boom, sweet. And really you see this now if you made these plots, right? If you had very nearly something like this, very nearly parallel, you get sort of symmetric. It almost looks like that. And then what's happening here is if you increase this slope value, it's going around like that. And actually, this height blows up more. So there's two things going on right here. If this is it's almost nearly parallel, it's quadratic, but it's actually really shallow. So I really should draw this looking like this because of that H2. So it's a very shallow, symmetric parabola where the x critical is almost up there. But as you get this situation where I draw down the H2, you notice the maximum pressure is dependent on over H2. Now you get this extreme jump, and the x critical is much far away from the halfway point. How far away? Well, you can always calculate it. And that's a slider bearing theory. All those expressions you wrote down are there for you. What was the point of all that? Okay. What was the point of all that? The point of all that is to show you that you go from just the h of x and how complicated things really kind of got. It's really, I'm trying to show you that, right? Where you have, before we did parallel, everything was hunky-dory, good, but just adding some functionality to this sliding plate, right, the actual solutions become far complex, and they tell you all the same things that scaling does. Okay? Really, this maximum pressure is behaving exactly as you would before. But what is important is, right, the maximum pressure, and the beautiful thing about this theory is you could calculate what the scale h is from the analytical work done in the equations. That's kind of cool, where you figured out that it's not really like the root mean squared of the x function of the h of x function you have. It's really this ratio of the integrals that tells you the exact characteristic h. And it's a characteristic h that lets you calculate the flow rate in your slider bearing. Lets you calculate. Very key thing in this class. What's important is figuring out ways to calculate things. Ways to calculate things. Okay. So that was the 2D. That's 2D slider bearing thing where you have this and then, right? Okay. Recognize where I essentially petered off from a general theory where I put some assumption on the h of x. once I said h of x looks like a line, I could then calculate all of these net forces, net pressures, pressure gradients. I could do it because I calculated. I could do it because I assumed what the h of x is. Once you do that, you can then get these ratios. Okay? Okay, the important thing is this is only right, these expressions with the k's are only true for when h of x is like really a line, or the model is that you have this slider bearing where there's just a slope. Okay? How useful is this? Well, even if you had a journal bearing, right? So here's, right, so, and then there's a bearing like this, and there's lubricant in here. So there's some eccentricity, let's say, right here. This is lubricant. Okay, lubricant in here. Well, this is sort of, right, this is the, and so, hold on. Okay, so here's a journal bearing where now it's a rotational problem. Not really a rotational problem. Everyone hates rotational problems. But, so then from the side view, I have this eccentricity here. And there's eccentricity, right, because when it starts off, it's going down. So let's say gravity's going this way. So now I can press a little bit here. Now I start to rotate. So if I rotate the inner one, let's say, what happens? Well, if you spread this whole thing out, well, there isn't, right, one approximation. Right, is the tangential one. You would just say that u is the radius times the omega, or the angular velocity of the angular velocity of the shaft that you're rotating it at. There's a lubricant in there. There's a lot more to this journal bearing thing, but maybe you have its tools maybe to understand what it's saying. And then really what happens here is you can kind of connect these two solutions. Okay, because we've already solved this whole problem pretty robustly. Okay, so I'll say this is solved. Solved to boot. And then what you get is you can then tell, right, you can then tell what is the maximum pressure happening on this journal bearing, what's the load bearing capacity of there with a lubricant in there. That is what, that's a neat thing. It tells you a force, right? It tells you some type of force happening in the journal bearing for you to estimate things, right? At a rotation, right, there's either more or less pressure happening at the very bottom of here, or the smallest contraction length. In fact, you have this pressure thing right here. Kind of like this. Right, and then really, right, you could also think of it as like this, where these are just symmetric. So this solution is called the half-Oseen equation. There are better solutions out there where someone realized like it looks like this actually, but you can just essentially figure out pressure. What's pressure? Right? Pressure is also a force divided by area. So if you think about forces, you want to find a pressure, and then you calculate some area. That gives you a force allowing to support some load. So that's the use of this theory. Now let's think about going 3D. Let's go 3D. How can I get this whole situation, but maybe get a more general scenario, right? And include some other things. So, right, we do the same process. I have a z here. I don't know why I did z. Oh, I wanted to maybe keep it with here. Okay, so now these are the equations after you rescale for a three-dimensional case, where now I'm allowing the side situation to occur. So, right, keep in mind we're instead of 2D, now I'm having a scenario where here's the y, and now I have like this before was my x, but now I have another coordinate, namely this z, That's why I use y. I should do x and y. I should do x and y here and leave this coordinate z. But because on my last examples I had this x, y, and the upper being and the height being y, I think I kept it this way where now I have z being this. So that's where this w thing is. So all the same scale things that we did in the first round of this lecture, you do again. Half hour? Can I do this in a half hour? Fuck it. Let's do it. Okay, you do again, but now instead of having a height like here, we could have some other thing. So now I have some surface. Let's say it looks like this. Okay, I always like to kind of draw these. It's always nice if you draw a surface to draw some geodesics on there, or lines that are going as straight as they can given the curvature that they are at. Okay. Okay, so now with this situation, what's important about Reynolds lubrication theory okay, so this is my flat plate, let's say. And here's one plate that's all variation, that has a lot of variation involved in it. That's what my theory can handle right now, is I have a flat plate and some surface above, but that it's solid. Okay, very critical for everything we've done right now is that this top surface is solid. So what that means, right? So meaning that there's no variation. So if I moved this plate around, all of the points on this plate are moving at the same speed. It's a rigid body. That's the definition of what rigid body motion is all points on that surface have to move at the same velocities or accelerate at the same rate. So that allows you to do a lot of things, really, and that's implicitly what I'm doing right now. If this surface does not wiggle, okay, it's not wiggling. It's not wiggling, or it's not a sheet that's like rubber moving around. It's that solid. Okay, so that really allows you to say the boundary conditions for this problem, right? So then here you have the same ones as before. Okay, and then here is an interesting one. So you could do the same here as well, right? So now for this W, you could go okay, some W component, and then also no slip at the height. Okay, so before, it's the exact same thing for W. So what I mean now is I could have a velocity vector here on the plate that's slipping. It's not slipping, sliding around. And this would be that U0. And that would be the component there. Okay, so if I have a flat plate, it could be moving in this dimension, right? And you can decompose it, where you'd have these now be a W and a U. So going back to the solid part, what does that mean? Exactly that. Exactly that. Saying, right, if I'm moving this at a constant rate, not a function of time, that means this boundary is a constant value. It will not change with x or y. Could it change with time? Fucking sure. Go ahead. One more thing, though. What else could I do? I could also vibrate this. So this would be the V component. So I could go up, down, up, down. I could have some oscillation happening on this 3D situation as well. Okay, so then that would be this. It can't be too fast. Why can't it be too fast, though? Why can that V not be super fast? Because we go back to when we got these equations, or what you do through the scaling. Through the scaling, you solve that there's some epsilon value, which is a ratio of here. So you can't have the scale v velocity be that big, or you would not obey that continuity relationship between velocities. It's very important to go back to these concepts where, right, you're not allowed to make this value enormously big, but it could be, you could have some oscillations going in there as well. Okay, so notice that this value now really has a different interpretation. So the up-down velocity, right, is really an h of t and x. In general now, this top surface, it could be a tumultuous mountain of, a terrible surface that's just got edges and stuff like that, but you could describe some type of surface. So now you have this situation where you have an x, y, and t. That is your slider bearing surface with a lubricant in there. Keep in mind there's lubricant between these two things. And there's lubricant between those two things because you're utilizing the viscous forces to move plates. You're using the fact that fluids can't support a shear to make it easier to move things. How easier it is to move things, exactly that ratio we did before. What's the net viscous shearing force over the net pressure? It's a coefficient of friction. Okay, so how do you go from here? Well, from here, this is the idea of integrating continuity. Okay, integrating continuity, right? So I have continuity like this. Okay, that's just continuity. I can't change it. I have to conserve mass. Stuck with it for life. But what I can do is I can integrate this entire equation. I can take this whole equation and go like, well, hold up a sec. What if I take this from 0 to my h value? So h. I won't put the functions in here, the function inputs, but realize that I'm saying integrate all the way up to the h. So it's a multidimensional integral, but all of the operations stick around. Okay, so move this one over the other side. Boop, bloop, 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 a bloop, ba-doop, a boop, boop, a boop, boop, a boop, boop, ba-doop. And so then the ba-doop, boop. Then you have this negative. I've just integrated them, moved one term over the other side. Integration is linear, so I can go boop, 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 and then move one over. I have a negative. Okay. I have to find that way. Okay. So here then, what is the integral of a derivative with respect to y while integrating y? Fundamental theorem of calculus says what? This is just the difference on the boundaries, right? It's actually Stokes' theorem generalized to all dimensions, actually, n doesn't matter. This still holds. The generalized fundamental theorem of calculus holds. The idea that what is the integration? Integrate the derivative as I get evaluating the boundary. Yes. Yes. So then here, and then you get that this is then just going to be a negative v. Now what is v? Connected all the way to there. So I have a dh dt here. Now handle this side. So this side is a situation where, right, can I commute the operation of integration and differentiation? Can I pull this out or in? Does it matter the order that I do these things? Well, let's just look at one of these terms. So if I were to take this out of the derivative, right, so what does this equal then? So I'm taking the derivative of this integral with respect to dy. Okay? Leibniz rule, or the idea is like Leibniz law of integration. I don't know what I can call it. Is what? It's this. It's this to this. Push it in, and then minus a boundary term. Evaluated at this. Yes. Okay. So, yes. Yeah. So first, just considering this, the way you do this integration is really an integration by parts. If anyone forgot integration by parts, I don't care. Retake Calc 2 then and look it up in a textbook and relearn it because it's very important. You would get this relationship that if I wanted to commute these operations, you would get this boundary term evaluated at the height. So then move this over to the other side, and you can actually have new terms to put where all of these integrations are. So I have one for the other one. And importantly, you have this scenario. Right? That's cool. And then what is okay. So then you have the difference, right? Same thing with the difference happening. And okay, and then you know what these velocities are, because at the value 1, you have that constant value, u naught, or some scale. So this integrate continuity, this. Okay, last step then is you then need to have the u, right? So you need the u, right? 0 to h, the u. Well, what is this? Flow rate q. Okay, so you need the flow rate in the flow rate in the x and the flow rate in the w. So you would actually have those rates, so you could, and let me just reiterate, that solution would be exactly the same. Those two momentum equations I have, you could integrate those two equations and you would get these relationships. You would have they're the same. So you have this Poiseuille part, dp dx, yh, and then you plus h, and here's the u. So now for the w, you would do the same integrations. This would be the same, only now you have a dp dz, dp dx, dp dz. Again, the third equation told you what? The pressure is not a function of y. So that's how I can write these things. So it's actually not partial. It's partial now. But you do know for certain there is no y input to this pressure function. And this would be the exact same thing. And this would now be a w. Okay? So that would come from solving what those are. So then you would then rewrite this integration of the continuity equation, use this law, move this over to the other side. Let me just do that explicitly. So that means this makes a plus okay? So in the continuity, I have this term. This term is equal to this integration. I get this u from this solution right here in terms of an h of x. Okay? I would take the integral of it, then take a derivative of it. Okay? Remember that, right? You solve for what u is, you integrate it with respect to y, and then you take the derivative of it. And then you evaluate this term right here. Same thing with the w. I would just have w's in this expression, and then d by dz. With all that in mind, you would then get this equation governing the three-dimensional case. Beautiful equation. And what's important, or I want to stress now, is for all of these types of problems, you can go directly to this PDE. Okay, it came from the Navier-Stokes, and all the assumptions hold, so you don't need to restart from the Navier-Stokes equations? Don't have room for this. I want to stress that, though, that you can start from here now. This equation you can start from for all of these types of problems. 46? Okay, so that's the beauty of this equation. Before, what I did when I first started this thing, I was like, let's do Navier-Stokes equations. Let's scale Navier-Stokes equations. Let's find the u velocity. Let's do some integration for q. Now what I'm doing is I'm doing a different thing. I'm starting from Navier-Stokes equations to derive some general equation for any type of problem, even in 2 dimensions, for some prescribed for some surface. Okay? And now, I have in symbolic notation, you can write it like this. You would have a 12, and then I write it like this. This is then a 6, boundary velocity dot gradient of h. And this is all equal to 1 over mu. Pressure gradient. This is just symbolic notation for what I've just written. Kind of helps you rationale what's happening in this equation more. Let me explain. That now it's in symbolic notation. Everything's sort of there right now, right? So you have this variation term where the up-down oscillation, maybe like it's accelerating a class, so you're trying to squeeze these two things together. Everything's in here. So this is speed of squeeze or push. That's this term right here. This term, a boundary velocity, okay, you just sort of define this, this UB is this U0, 0, and then transpose. So this is a vector of these constant velocities. Okay, this can be slightly augmented where these could be functions of time. Okay, so now I have a vector as a function of time, still obeys right here. So now it's this vector, and now you dot product that with the gradient of your surface. So gradient of your surface. Okay, so if we're areas where the tangent plane is really steep make this term very large. Areas where this term, right? So the areas where the tangent plane on your top surface is basically flat, neglect this term. Okay, so if it's really flat, this term it's not really in there. And then this term is also important, right? So this term, and then this term is pretty cool. It's cool. You have this divergence of the pressure gradient, scaled up by cube h. Really just a lot more is in there to internalize now if you're trying to solve problems with it. Okay. Right. So here's the movement of these plates, and there's an interaction now, right, between the curvature of the top plate and the sliding plate, right? And you see that because, right, the lubricant has to obey no slip here, so it must be moved along out here. But there's a scale up by the curvature happening in the top plate. So there's an interaction in there. It plays itself out in here. And then this term is the viscous force, right? All the viscous terms are encapsulated in this term as well. And it's cubed, so it's nonlinear. Important, what is this equation solving for? If I had an exam in class, this would be a large point question. And seemingly, people have a hard time with this. What is this solving for? What in the heck is this equation solving for? right? What do you get if you have the solution? You get the solution is that, right, this is the solution for the pressure field. The pressure field has a partial differential equation that governs what it is. So just like in the slipping bearing situation where I prescribed the h, I prescribed what this h of x was. It's the same thing happening here. You give me an h of x, y, and t, and I'll tell you the pressure. You tell me what the h is. I can do these operations, no bada bing, bada boop. But then I can figure out, right, numerically or in special cases analytically, what the pressure is in this whole field. And I'm sure you all can suspect, right, if this was flat, you would just get this, right, an elliptic bulb, right? So really just a rotation of a quadratic term would be exactly what you get. But this is more general because you can prescribe any h of y and z and solve for it. Can you go the other way around? What do you think? Anyone? Could I go the other way around? Could I just prescribe a pressure gradient and solve for what the h of x, y, and t is? Good question. Hello, hello. Who's that? Classroom. Hey, is everybody feeling starts at 4? Is Jacob running the thing? All right. Okay, I like this equation, and the beauty of it is it says a lot of things in here. So right now, immediately, let's talk about viscous adhesion. What is viscous adhesion? You've certainly, I imagine, have felt viscous adhesion. If you've ever gone to a party in your early college days or in your high school days, and you played beer pong, let's say, and you were playing and the cups were on the bottom, right? At some rate, if it was a very flat cup, you can try to pick it up, and it seemed like it was stuck for a little bit. Or if you had a lubricant and you had two very, very smooth surfaces, and you just slid them together like this. So you applied shear and moved two very smooth blocks together. Use a motor oil if you want, but very smooth surfaces, slide them together, and then try to pull them apart. It is enormously difficult, right? Especially if the surface is very smooth. That is explained in this equation. It is explained perfectly. So all the assumptions are there. Viscous adhesion means I'll have now a normal part, right? Let's say let's make it flat. So if you make this flat, what happened? If you make it flat, and this term goes away, there's no tangent plane, But the idea is you get a lot in there because if it is a flat surface, here's what you get. Okay, this is this dH dt. This term is my squeezing or pulling velocity. If I'm trying to accelerate these two plates apart, I'm trying to move them apart at some speed, right? That's the dH dt. Excuse me. The dP dx now, I'm after this thing. You can get it by just integrating a bunch. So dP, I have a pressure gradient, and amazingly, you have this situation. This. So this is a square, you do the 2D case. So if it's a perfect square and everything's symmetric, you can just do the 2D case, and that would make this just a one derivative operator, not a gradient operator. But the scaling relationship still actually holds, which is what's important. Scale is always important, right? Scales always tell you what is actually happening, right? Because it tells you what? It tells you the pressure gradient is 1 over the freaking gap length cubed. So if H is really, really tiny, like on a micron scale with lubricant in between it, okay, this is huge because it's a tiny number, right? The faster you pull it, the faster you're trying to pull two plates apart. Again, remember, we're trying to describe now two blocks being pulled apart with lubricant in there. Okay, viscous adhesion. somehow, even though the lubricant is not a glue, it's not fusing together. It's not fusing together with the surface at all. What you've done now is you've had the situation where if I do this, if I'm pulling apart this way, it is an incredible amount of force needed, right? Pressure is a force divided by area. So you could normalize, you could multiply this whole thing by the block area and to figure out what the force is required, right? Scale length size, so that's kind of important as well. If it's a more viscous liquid, you'll require more force, so it's almost like a glue. This term is saying the more viscous your fluid is, the more adhesion you're going to get. The faster you try to pull it, the more adhesional force you'll have. But this 1 over cube term blows up and just screws you up. Same analysis will tell you one thing, right? It tells you that the shearing, we already did this, right? We already did the bearing design before. What was that tangential force over the normal force? It's enormously small. And it's much easier to move these blocks this way than it is this way. And that's exactly calculated by that K value. It's exactly quantified now by that lubrication ratio. OK. I have 2 more pages left. And I have 2 more pages left because I want to do it the right way now. What I say the right way. So we started off by that slider bearing problem, but I did it all through the Navier-Stokes equations. So while I'm late, I think this is very important. I think it's important for you to see that now that you've done work and you've done the mathematical analysis to establish a new governing equation, this equation is called Reynolds equation, okay, partially and all. Now that you've done that work and you are in the scenario such that all the assumptions hold, you go directly to that bad boy. And then you do solutions. And it gets you there a lot faster. Okay, so I spent a lot of time talking, but I want to do this, so bear with me. If anyone's even still watching these lectures. Hope you are. Anyone out there? Okay. So before I go on, there's one more thing about this equation that is friggin' beautiful. Okay, is this 1 over viscosity term here. Now, we said that the Reynolds number had to be moderate. That means it could be like 25,000. It could be really, really big. But if the H and L is really small, let me write this stuff down. I'm going. Right, moderate. So this could be like, it could be very large, right, because of the U naught. So be going very fast. Okay, so be going very, very fast. But you could still be in this Reynolds approximation, right? Really even just with as much less, right? This is sort of the key thing. So it's sort of really, however large your Reynolds number is, you could even calculate what your aspect ratio has to be, or how thin your gap is to use these equations. If you can't do it in a design way, then oh well, use other methods. But sometimes it's not that hard to really get here. You could really get a gap length. You could machine surfaces to be even finer to achieve this. Okay, so then this could be really, really small. I mean, we already saw if it's 0.008, if it's like a 1/64th of an inch, very doable, right? You square that bad boy, it gets really small. But there is a problem with this that I did not bring up, that I did not talk about, and that is the issue of heat. Okay, so I thought you said if it's moving very fast, most of it's kinetic energy. Not in this case. In this case, because the length scale is so small, most of the energy is work done by friction. So in terms of energies, if it gets even faster, what's happening is now it's getting hot. Now your bearing is moving so fast that it's having to turn some of that energy into heat. Now, what's the problem with heat? And then it could also, so essentially you could also have, right, work and then a heat. Okay, right. The energy could be the energy is either the energy in this flow is either characterized by it's either the work done by friction or it's characterized by the heat being produced in it. Essentially, you're moving this thing so fast that there's so much energy that's even going into moving the energy is even going into the internal vibrations of the molecules in the liquid. What does that mean for us? That means that if it's going really, really quickly, how should I say this? Okay, that means this. If it's heating up, that means that the viscosity is changing. Okay, you have a changing viscosity now because of the internal heat that's being generated in there. The higher the hotter a fluid is, the less viscous it is. It's easier for these molecules to slide past each other the hotter it is. And that would be encapsulated by this. Okay, so you really would have this scenario where now your viscosity value, okay, will be a function of the temperature in the plate. Let's say it's a function of time. You have that scenario right here. The beauty, again, of this equation, right, is if you model now that changing viscosity. If you say, okay, I'm accelerating, I'm going very, very fast, and I know experimental, let's say, that's heating up. My bearing is going to heat up to some temperature. I'll have some transition of the viscosity going from mu naught to mu final, let's say the steady state temperature of the system. That would give you viscosity at two endpoints. You could characterize what this is by heat analysis. All you do is now this is just 1 over that value to the t. It's now a function of time. So now same scenario. You tell me the h is an x, y, and t. You tell me the mu of t, solve for the pressure field. Pretty cool. Okay, so now with this equation, let's redo the same problem. You just do it in one page. So this is my problem. We'll have constant viscosity. Constant viscosity is going to hold. And then we'll get at it. Okay, so constant viscosity holds. Everything we have that V naught will be 0, which does mean that the dH dt is 0. We'll go 2D. That means that this is going to be zeroed out as well. What else am I going to put up here that I'm going to jam to this equation? I'm going to say what? Same things we had before. This scales like this. Okay, and then H scales like H1. So I'm doing this same problem. What I mean by the same problem is I'm going to do the same situation where I'm going to do this line thing with the nasty solutions and a dead fucking pen. Ugh. Okay, redrawing just this problem. I don't want to draw all the things, but I'm doing this problem again, but I'm using this governing equation. Bear with me. I know I went over time, but I feel like I'm just talking to myself these days, so whatever. I'm having fun. So now I have a pressure, and you do this pressure where you go pressure star. P is around some reference pressure plus the non-dimensional pressure. So like that. So this is exactly what we did before. No, I should have the H. Okay, this is the pressure scale. Okay, so the pressure scale is still the same thing that you get from the equations. This one, I'm going to use H1. You could use that h that you calculate from that ratio of integral quantities, but like let's just say for the non-dimensionalization we're going to use these scales. Okay, so first thing I'm going to do the same thing I did before, where I'm saying that the h is a function, looks like a line. Well, in the non-dimensional case, so non-dimensionalize the h function, you get what? You just get it looks like this. Okay, where now m is equal to h1 Okay, kind of shows you why I picked h1. I picked h1 because it's the largest value of h I have. For scales, it's always usually normative or naive to always just pick the largest. Okay, so I have my non-dimensional h function. You have all the non-dimensional et cetera. So now just jam this all into this equation. This term's out because the slider bearing is not moving up or down. And you get only one term left over. Nope, this term's out as well. And then you get just this term right here. Yes, and you get that the viscosity doesn't matter. So even showing you something that now this doesn't go out. I have one term left over. I'm an idiot. Okay, you have one term left over here. You can show what it is. H, you got to divide it out. One sec. That's right. Okay, this is everything in there. Okay. Because this normalizes to a 1, because I only have one velocity in there. So this would just be a 1. And I'd have one derivative term, and then the 6. Then I have one derivative on the outside, cubed d per dx. Okay. So then you integrate. Integrating. And then there's just some integration constant hm, which you don't quite know actually yet. So there's just you integrate it, so you leave it for the constant. I'm calling it hm for a reason later. What next? So then next is you integrate again for this dp dx. Okay. Notice that, right? Importantly, remember that we're not solving for h of x. We know what it is. It's just this very simple linear function. 15 minutes left. Okay. Keep along. You're really after this friggin' thing. You're after that pressure gradient, but we're doing it the non-dimensional way. Okay, so you can get that with another integration, and it's just a very simple non-dimensional parameter, m. So you see the slope thing popping up everywhere. Makes sense. It's telling you that the slopier that your line is, the more difference your pressure gradient is going to be. Already, I hope you see there's just all these functions are just a lot nicer, and you can even do this integration by hand if you want. Okay, so then what you do is you say, yes, so then you go, okay, well then the non-dimensional pressure at 1, so this is at the exit, say it is 0. Set your gauge reference pressure here. Okay, it's the same thing as going, okay, this is boop, boop, 0. Free to do that. Okay, and then from here you can figure out what this is. So then you have here, that just means that h m star is going to be equal to 2, 1 minus m, 2 minus m. Here's m. M is a parameter describing the slope of this line. Okay, so it's a slope parameter. So you have 2hm there, and then you get the final non-dimensional pressure function, again, by just plugging everything back in. So then you have bum, 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 1 minus the m. It's going to be 2 minus the m. 2 minus this m star. And on this one, then I get 1 minus the m at. Again, I've done all the same stuff. I'm just saying I started from the general equation, did my non-dimensionalization, and just all the integration steps is just a lot easier. Things are easier to plot. It's even easier to figure out what this dpdx, or the critical x, is. Okay, so then you have that the maximum pressure is equal to a slope value. This, and you can even calculate now this. These are just simpler expressions. Keep in mind what this looks like compared to those logarithm k values I have, which just comes from me integrating, right, and getting things. This idea from going this way and using non-dimensionalizations, it certainly looks better, right? So I get the same graph for pressure in this slider bearing, right, where here is now my non-dimensional, and here's my non-dimensional pressure, okay? And then now you get the same relationship where you have like that, where there's this line increasing m values. Beautiful. Even a better idea of how this maximum pressure looks and behaves, right? Pretty cool. Now it's just all this little m variable you have. Okay, I want to remind you that m is that. Okay, calculated m for any h2 and h1, and here are your equations of the pressures. And you can do the exact same thing with the net pressure force and the net shear force. You can do the exact same ratios. It's just nicer if you do it this way. Okay, so please study and look at that wonderful Reynolds equation. And just, pretty amazingly how complicated things got just from us adding this top curvature here. What's important is that solid and the flow rate through it had to be constant, and there had to be no slip right here. Okay, so next lecture, what do you think I'm going to do? It's called surface tension, but we're a little prepared, right? So next lecture I'm going to do is I'm going to say, this is a wiggly surface. This is going to be some rubbery sheet that just wobbles around. But I'll need extra physics to tell me how does it wobble and what makes it wobble. And that's the idea of surface tension of a fluid. So there's another hidden energy source in fluids that I didn't tell you about. So remember, we have our little pots of fluid, right, that we can pour our energy into, and they can only take up so much. So there's another one, right? So in terms of energy, there can be this idea of work done by friction, work done by viscosity. There's kinetic, okay, and there's rotational at the bottom. And then there's even surface energy. Okay, there is energy in the surface and interface of a liquid. And that energy is a source to drive flows, which is a fascinating subject. It's a very difficult subject, but it relies in the same world. Same ideas are behaving right now, where the fact that there is a top curvature allows for allows for flow rates and viscous forces to have effects. Okay, I went over. Hope you maybe appreciated. Maybe the whole point of this goal, this lecture, was to show you when it comes to fluid analysis, it is better, I think, to do the work to derive a much general equation, which is called Reynolds equation, and then work on that instead of starting from Navier-Stokes every single time. So what do we have so far? We have the Navier-Stokes equations in full 3D, always got those. From that, we have the boundary layer equations, which we derived earlier, always good to derive those. We now have the Reynolds equation, right? Always good to have that as well for the problems at hand. We have the Faulkner scans, ODEs. There's governing equations we have that govern whole classes of flows. And that's the beautiful part about fluid dynamics, I think.